One is to test the hypothesis. Today, we're going to do two things. The first thing we will do today is to test the hypothesis for simple linear regression. And then we will go into multiple linear regression. Now, in looking at simple linear regression, we're going to go through the calculations of a hypothesis test for a linear regression. And then we'll then apply the method to multiple regression so that you will have an idea how to proceed with the assignment. So I'm going to share screen, and I'm going to go straight to simple linear regression. Besides that, when I'm done, I'm going to post the lectures from the previous semester so that you all have the benefit of previous lectures in this class and see how things are going or how things are done, not how things are going. So you see how things are done, and you feel free to play them and do the homework assignments. So I'm going to pull up the screen first. Okay. All right, so can you see the screen? Hello?
Yes, Professor.
Okay. All right, now the screen you see here at the very top is hypothesis test for two populations, but we're going to go straight into regression analysis, but you also see what we did for two populations if you care for it, okay? So what we're going to do is we're going to apply the concept of regression analysis to estimate the linear relationship between two variables, okay? And then we will evaluate the significance of the slope of the regression line. And what does it mean to evaluate the significance of the slope of the regression line? I believe we mentioned a little bit of it the last time, okay? For example, if you bring any two set of values of a dependent and an independent variable, you will always, be able to find an estimate of a relationship, okay? But it does not mean anything. And I raised the question, suppose that you stand at the intersection of Bedford and Eastern Parkway and count all the vehicles that pass through the intersection, say every hour of the day for 10 hours a day, and then maybe you do it for 2 or 3 days. And so the first hour, you notice 30 vehicles, the second hour, you notice 40 vehicles, and the fourth hour, you notice 16 vehicles, and so forth and so on. And so for 20 hours, you take note of that. And each time you count the number of vehicles that pass the intersection, you pick up your phone and call the hospital downstate and ask how many new babies were born. Okay, and they give you, and you write it down. So the number of new babies become the dependent variable, and the number of vehicles that cross the intersection at Bedford and Eastern Parkway will become the independent variable. And so if you do an estimate to see whether the number of babies born in each hour is dependent on the number of vehicles, you will find an estimate of a relationship. You will. But you know very well that the number of babies born does not depend on the number of vehicles that cross Eastern Parkway. There's no relationship. And so what we do then in the regression analysis is to do a test of hypothesis to see if such a relationship is real, okay? And so we will talk about what that means and how we reach a conclusion whether such a relationship is real once you do your estimate, okay? And then we will evaluate the regression equation's ability to predict, okay? or we will use regression equation to do a prediction. All right, so like we said, in regression analysis, we are looking at the relationship between two variables, y and x, okay? The dependent variable is y. For example, how much you spend on food is a dependent variable, okay? An independent variable will be how much income you have. It could be the size of the family, okay? That's an independent variable. And naturally, we know that the bigger the family size, the more money you spend on food. And so a dependent variable would be how much the family spends on food. The independent variable, x, will be the size of the family. We ask ourselves, what is the size of the relationship? Or what is the nature? The nature of the relationship, for example, is it negative or positive? Or maybe there is none, okay? Negative relationship, positive relationship, or none, okay? Now, a good example of a negative relationship is something that we study in economic theory, that the quantity demanded of a good depends on the price of the good. The higher the price, the lower the quantity demanded. And so we have a negative relationship. One goes up, the other goes down. Okay. We also estimate the size of the relationship. Okay. For example, when you think about, say, family food expenditure and family size, you ask yourself, for each additional 1% in family size, how much additional does the family spend on food? For each $1 increase, 1 unit increase in the price of a good, how much is the quantity demanded reduced? Okay, and then finally we ask ourselves, how strong is the relationship? For example, we know that the larger the family size, the more the expenditure on food. But the question is, how much does family size actually affect the amount you spend on food? How much? Not necessarily. Now, remember that the family size alone would not be the determinant. There could be other determinants. For example, the income of the family. Secondly, the habits of the family. Okay, some people eat a lot, some people don't eat a lot. Okay, so what percentage of changes in the dependent variable is explained by changes in the independent variable. And we will, as we go, we will show how to reach such a conclusion. Okay, and so the process is to estimate the equation of a line. Okay, and the equation of a line, like y is equal to a plus bx. Now, a is the constant, okay, value, which is to say, even if x is 0, okay, even if x is 0, y will have a value, okay? Even x is equal to 0, y will be equal to a, okay? Even if x is 0, right? For example, you think about the price of a good and the quantity demanded. Even if the good is free, if the price is 0, people will still buy a certain quantity, but it will be limited, okay? Now, B represents the slope or the rate of change of x and the rate of change of y when x changes by 1, okay? The rate of change of y when x changes by 1. So in that case, if x changes by 1, y will change by b. Y will change by b. For example, in the relationship, y is equal to 10 plus 5x. This is a positive relationship. If x is 3, y will be 10 plus 5 times 3. Okay, so that means that y will change by 3 times 5, and so 5 is the rate of change. Okay. Okay, now when you look at the equation y is equal to 25 minus 2x, this is a negative relationship because the coefficient of x is minus 2. Here, this is positive because the coefficient of x is 5. So if x is equal to 3, then y is 25 minus 2 times 3, because the coefficient here of x is 2. And so when x is 3, 2 will multiply 3, and you have 19. Okay, so let's now look at what we do in regression analysis, because we are going to estimate the equation of y is equal to a plus bx. And as we said last time, because we are dealing with statistical data, the relationship is not perfect. And so we use a hat to estimate a, and we use b hat to estimate b. So how do we proceed with that? Okay. I'm going to provide an illustration. Okay, and we're going to use an example. This is sales and sales calls. Now we are looking here at a situation we are dealing with sales persons, and so the more sales calls the salesperson makes, the more sales they are likely to make. Okay, and so the sales will be the dependent variable, and the sales calls will be the independent variables. I'm going to label them. This is the independent variable, and the sales will be the dependent variable. Okay. All right. So let us see. Going to all right. So now the formula, and I'm going to move things around so that we're consistent. All right. So we use a formula. Remember, we're trying to estimate, using ordinary least squares formula. Y is equal to a plus bx, and the formula will be the summation x times x bar times, x minus x bar times y minus y bar divided by the summation x minus x bar squared. So how do we get this? And I'm going to illustrate this bit by bit. Okay. And so we have to calculate x bar, we have to calculate y bar. And so we're going to do an illustration. As you can see, I'm going to go through an illustration, and I will then I will use a different example to do the illustration. So I'm going to stop share this for a minute, and then, but like you see, we have y minus y bar, we have x minus x bar, and we're going to be dealing with these summations. Okay, so let us see how we get to the summations. Hello, are you seeing my new screen?
Yes, I see the Excel spreadsheet.
Okay, thank you very much. Okay, so you can see here what we're going to do. remember we said we are going to take the summation of x minus x bar and the summation of y minus y bar, and then we're going to multiply x minus x bar times y minus y bar. All right. So I'm calling x bar xb, I'm calling y bar yb because this is Excel spreadsheet. So the first thing then we do is to find x bar, which is the mean of x. So let us find x bar. Okay. So this is x bar. Okay. We find the average. Okay. We find the average of x. And we do the same thing to find the average of y. So then we calculate x minus x bar. So we take each value, this is x, so 7 minus 7.58, what have you. And so we take 10 and we subtract 8 from that mean. And so we go equals K4 minus K33 $K $33. Okay, as you can see, that's highlighted. And so we do that for every value of x. All right. If you sum that, you get a 0. And then we do y minus y bar. So we have y here, the maintenance. And so what are we trying to estimate here? We're asking ourselves the question, the cost of the maintenance of a vehicle, does it depend on the age of the vehicle? Okay. We know theoretically it is so, but we're trying to illustrate it using actual data. So maintenance is the dependent variable and age of the vehicle is independent variable. So we take 329 and we subtract the mean of y. And so we do the same thing here. Okay. So this equals M4. No, I'm sorry. M4 L4 minus $L $33. You can see 33 is highlighted, L33 is highlighted, and that is just a way to fix the location. So we get those numbers, and if you sum, you get a 0. So that means our calculation is making sense. All right. So now, if you go back to the formula we said is summation x minus x bar times y minus y bar. So we have to multiply the column M by the column N. Okay, x minus x bar times y minus y bar. We have to multiply the two, and so we'll say this is equals, okay, N4 times M4. All right, we'll multiply the two, and so we have that. So we sum. So we get that summation. All right. And now we say we're going to divide by the summation x minus x bar squared. So we take M and we square it, which is to multiply by itself. So this is equals M4 to the power 2. So we square it. All right. And so we sum that. All right. Okay. So now we're going to use that to estimate B hat. So for now, I'm going to save this. Let's see if we can find our example here. I'm going to share screen now. We're all right.
Yep. PowerPoint. Got it.
All right, but this is not the one that I want to share, so I will share the right one.
Oh.
All right. So this is the Buena boss problem. Okay. I'm going to pull up the formula again.
Okay.
All right. All right. So this is the formula. Okay, so you see, we said we're going to estimate A using A hat. We're going to estimate B using B hat. So as you can see from our formula, our original formula, okay, the summation x minus x bar times y minus y bar is 6672, okay? Here it is here. Okay. See, I'm going to try to reduce this. It's not showing. I'm just going to
Reduce the zoom instead of 100.
Oh, yeah. Boy, thank you so much.
Yeah. There we go.
All right. See, like I say, 2 hands are better than 1.
Yep.
All right. So let's see, but it's still not yielding its numbers.
The numbers are looking for the bottom, right?
Okay, so what I'm going to do is I'm going to pull up. I'm going to pull up the Excel spreadsheet. So, okay, let's pull up the Excel spreadsheet. Okay. All right. So this is where we had the summation x minus x bar times y minus y bar, but this is a different sample of data. But you use this summation here that we obtained, y minus y bar times x minus x bar. Okay, not exactly the same sample, and so these numbers will be somewhat different. But those are the numbers that we are using, and so the numbers are here. Okay, so you see x Okay, so this is the same numbers. That's correct. Summation x minus x bar times y minus y bar was 3,198. All right? That's what we had in the Excel spreadsheet. And the summation x minus x bar squared was 205. And so the slope, okay, the slope of the function is 15.59. And so we calculate a hat, which is, that is the formula for a hat, y bar minus b hat times x bar, and we have 329.94, okay? Yes, so that's the same problem. If you look at the okay, so you see the 3,198 is here, and the 205 is there. See that?
Yep.
Okay, and you see the mean of y and the mean of x. And so you see the b hat is 15.59 and the a hat is 329.39. So let us now try to give meaning to all of that. Okay. Let's give meaning to all of that. So what does that mean? So now you use the a hat, which is 329, and the b hat to create an equation, okay? Remember the equation we had, y is equal to, what do you call it? A plus bx, right? So this is the model equation. Okay, the model equation is that y is equal to a, which is your a hat, 329, plus b, which is your b hat, times x, which is the age of the bus. So y represents the maintenance expense, and x represents the age of the bus. So what does this mean? What does 329 mean? Okay, 329 simply means the constant value, a. Okay, now I'm going to try to let's see. Let's do it here. Okay, you remember y is equal to a plus b times x. Remember that? This is the equation. Okay.
Yeah.
So a is represented by 329. That's your a hat. It's a hat here, right? And b is represented by b hat, which is 15.89. So 15.89 times x. All right. Okay. So what does it mean? Now, a is a constant value. It simply means that the base cost of maintaining a vehicle is at least $329 per year. All right. Even if you don't drive, even if it's a brand new car and you don't touch it, the base cost of maintenance is $329, because you change oil, you run the engine every now and then to make sure that the engine is still working and all of that. And then for every 1 year additional in the age of the bus, you're gonna, the cost of maintenance will increase by $15.59. That's what it is for every additional year. So a bus that is 1 year old will cost you $329 plus 15.59. Okay, a bus that is 2 years old will cost you $329 plus 15.59 times 2, which is about $31. Does it make sense?
Yes, it does.
All right. So this is what the regression equation explains to you, or helps you to explain. You'll be able to estimate how much it will cost to maintain a bus. All right. Now, we have now estimated the nature of the relationship, which is that there's a positive relationship between the maintenance cost and the age of the bus, which is to say, the older the bus, that is, as the age of the bus increases, also the cost of maintenance of the bus would increase. So for a bus that is 8 years old, if a bus is 8 years old, the cost of maintenance will be 329 plus 15.59 times 8, which is 454. Okay. So now that we have estimated the nature of the relationship, which is it a positive one? Is it a negative one? What is the size of that relationship? Now, the next thing we ask ourselves, what are the other factors that could affect maintenance, which is to say, what percentage, to what extent does the age of the bus explain the cost of maintenance? Okay, and we have a formula, okay, and the formula is called the coefficient of determination. That is what the nature, I'm sorry, the, call it, how strong is the relationship? That is what the coefficient of determination explains. How strong is the relationship? All right. And so now, how strong is determined is calculated using what we call a coefficient of determination. Okay. And it's called R squared in regression analysis. And so we use B hat times this formula here, which is summation x minus x bar times y minus y bar. We already have that, but we do not have y minus y bar squared. Okay, so we're going to find that, and that is what we're going to do next. So I'm going to calculate y minus y bar squared. It's already here. Okay, but we're going to do it again. See y minus y bar squared. And so I'm going to calculate it. So I will stop share this. Let us find y minus y bar squared. Okay. Okay. So this is y minus y bar squared. All right. So we take y minus y bar in this column n, and we square it. And so it will be equals and 4 to the power 2 all right, and so we sum it. Okay, we sum it and we get 12,1142. All right, so let's go back to oh Lord. Okay, thank God. All right. All right. So we can see it's 12,1142.79, and this is y minus y bar squared. And so we say, and the answer we get is 0.4118. So we're saying that 41.418% of changes in maintenance is explained by changes in the age of the bus. So that means that there is still 58% or 59% of the cost of maintenance that is explained by other factors that we don't know. Okay, it could be the locations where we drive the bus. Okay, if we drive a bus in very bad roads, and so what happens is that you get one bus that is 8 years old and another bus that is 8 years old, but the cost of maintenance will not be exactly 454. It could be 459 for one, it could be 500 for another, because maybe bus number 2 will drive in rough roads, okay? Because bus number 2 is driven by bad drivers who abuse the bus, okay? And so they create more problems for the bus. All right. So now the next thing that we have to do is to test a hypothesis of the slope, okay? That is to say, it's possible that the age of the bus has nothing to do with the cost of maintenance. It's possible, okay? So we just want to assure ourselves that the age of the bus is what affects maintenance. So let us look at the equation again, okay? The equation is y is equal to a plus bx. So it's possible that this b is equal to 0, which means that the age of the bus has nothing to do with the maintenance. So in that case, b will be equal to 0, okay? And we reach that conclusion that b is actually equal to 0 by a test of hypothesis, okay? And so how do we test that hypothesis, all right? So we state a hypothesis, okay? We state a hypothesis. The null hypothesis will be that b is equal to 0, which means that the slope of the regression is 0. Or the alternate hypothesis, okay? The alternate hypothesis will be that b is not equal to 0, which is to say that the slope of the regression is not equal to 0. And that means that truly, truly, the age of the bus is what explains maintenance, okay? So how do we go about doing that? That is what we're going to do next, okay? Just give me a second. Okay. All right. So how do we go about doing that? Okay. Now, when you test a hypothesis, as you already know throughout this semester from earlier lectures, we select a level of significance. Okay. Once we select a level of significance, we identify a test statistic. It could be Z if the sample is large enough, or it could be T if the sample is small, which is if the sample is less than 30, then it's a small sample, and we use the T distribution. All right, so this is another example, and this actually should go up here. Okay, just give me a second. This is okay. It's another example here, so we'll put it in the right place. Okay, if your bus is 9 years, the maintenance will be 470 instead of 484. All right, so now we're going back to test of hypothesis. And so once we state the null hypothesis, which is that b is equal to 0, and the alternate hypothesis is that b is not equal to 0. If b is 0, that means that the independent variable has no effect on the dependent variable, which is to say age does not affect maintenance, okay? But if b is not equal to 0, okay, that means that the slope of the regression is not 0, and therefore age affects maintenance. All right, and like we said, we're going to select the test statistic, okay? So for this particular problem, okay, so the test statistic we're using here is a Z, and so we calculate a Z, okay? We calculate the Z value, and the Z value is calculated by taking B minus B hat, which is if the the B hat is what we calculate. The B, the theoretical B, is the null hypothesis. Okay, so this is going to be a 0. Then we calculate what we call the standard error of B. Okay, we didn't go through that calculation, but we use the standard error of B. So Z is B minus B hat divided by the standard error of B. Okay, and so the calculated.
Just understand that.
The calculated standard error of B from our model, which you see, this is the formula for calculating the standard error of B. And so we get that calculation, and I'm going to show you how to use it for an equation when you're given all the numbers. For example, again, this is another example of if the age is 7, but let us go to what our problem is now. Okay, so this is how we calculate the standard error of B. And so we're going to use that formula. Okay, let's see. So it looks like it's B hat. I'm going to try to get the standard error of B. So now that we don't have this, I'm going to calculate one so that you can see what we're doing. Okay. So I'm going to take this formula and I'm going to calculate it here. This is the standard error of B. So let's get y minus y hat squared. Let's see if we have it up here. Okay, so we don't have it. I'm going to calculate it. Okay, so you can see how it's done. Okay, it's going to be the square root of y minus y hat squared over n minus 1 times the summation. And this is a summation there. So let's correct that notion. All right. So we have corrected that. And I'm going to correct it also in another place. Okay. All right. So the formula is correct. All right. I'm going to stop share for a minute. So bear with us. Okay. So we're going to calculate y minus y hat. Okay. And so now we don't have y hat. I think we have to use a different formula because we have to calculate y hat for every y. Okay. Y hat will be very, very long formula. So I don't think that it's going to serve us any purpose to start working on it now. So let's see if we can use another example. But I'm going to work that out and show it to the class. Okay.
Okay.
Oh, okay. Wait a minute. The summation y minus y bar squared over that. So that's easy to do. We're going to use we're going to use another example. Okay. This is, I'm going to reorder some of these so that we're consistent. So now we're going to do another test of hypothesis. Okay. This is an example that we're going to use. Okay. Here we estimate Y, okay, for family size and food expenditure. And so in this case, we estimate that food expenditure depends on family size. So for each additional person in the family, there's an additional 41 cents per dollar for food, and we spend $3.37 for basic food. Okay, and the standard error of B for this particular problem is 0.048. We're using a level of significance of 0.005 and a Z star. The Z star for 0.005 is 2.576. You can look that up. Okay. The null hypothesis is that family size does not matter. Okay. That is, family size does not affect the amount spent on food. And so that is the null hypothesis. The alternate hypothesis is that family size does matter, which means that family size does affect the amount spent on food. So we calculate a Z, which is B minus B hat, which is 0 minus 0.414, divided by the standard error of B hat, which is 0.048, and we find that Z is 8.62. Now we use a decision rule that if Z is greater than Z star, then we reject the null hypothesis that family size does not matter. Okay. Now if Z is, let me separate this so we don't cause confusion. If Z is less than Z star, then we cannot reject the null hypothesis that family size does not matter. So what is our conclusion here? Our conclusion is that since Z, which is the calculated Z, is 8.625, is greater than the hypothesized Z star of 2.576, so we reject the null hypothesis. We are rejecting the null hypothesis that family size does not matter. Okay, and therefore we do conclude that family size matters, which is we conclude since we are rejecting that B is 0. Therefore, we are concluding that B is not equal to 0, which means that family size does matter. All right, is that clear?
Yes.
Okay, so we're saying that family size does matter, and so this is our conclusion, and that's our test of hypothesis. I'm going to take this out for now so that we don't cause confusion. But you have learned how to test the hypothesis. You have learned how to calculate the coefficient of determination. And so next week, we will now do multiple regression analysis, and in which case we're going to be looking at a dependent variable that depends on more than one variable. Now, remember here, we looked at family size and food expenditure. We looked at maintenance expenditure and age of the bus. But it could also be that maintenance depends on age of the bus. It depends on how rough we use the bus, okay? It could depend on the kind of bus. It could depend on the make of the bus. And so all these factors could combine to affect maintenance. So next time we're going to look at multiple regression, and then we're going to also test a hypothesis for multiple regression. Is that clear?
Yeah.
Okay. I think we have had enough for today. And so, yes. So you can digest this and try to do your homework assignment. I will keep moving the deadlines for the assignments to make sure that we know what we are doing.
Okay. Thank you,
Okay?
Professor. Yeah.
All right. So I think we have had enough for today. So let me save this for October. Okay, so this is what we're going to. Okay, all right. So I hope you enjoy your evening.
You do too.
All right, so I'll see you
Bye.
next week. Okay, good night.
Bye.